Historic discovery, K2-18b reveals potential biosignatures paving the way for future exoplanet research. Introduction. On April 17, 2024, a landmark announcement from NASA highlighted significant advancements in the search for extraterrestrial life, focusing on the exoplanet K2-18b. This groundbreaking research, driven by data from the James Webb Space Telescope JWST, has unveiled potential biosignatures in the atmosphere of K2-18b, thereby reshaping our understanding of habitable environments beyond Earth. Overview of K2-18b. K2-18b is an intriguing exoplanet located approximately 120 light-years away in the constellation Leo. First discovered in 2015 by NASA's K2 mission, this exoplanet is approximately 8.6 times more massive than Earth and orbits a cool dwarf star within its habitable zone. Its unique characteristics, particularly the potential presence of liquid water, make it a prime candidate for the search for life. Key findings. Recent investigations using JWST revealed the presence of carbon-bearing molecules, particularly methane and carbon dioxide, in K2-18b's atmosphere. These molecules are crucial indicators of potential life-supporting conditions. Notably, the absence of ammonia reinforces the hypothesis that K2-18b may have a hydrogen-rich atmosphere above a water ocean. Most significantly, a tentative detection of dimethyl sulfide DMS was reported, a compound associated with biological activity on Earth, particularly produced by phytoplankton. Integration of research findings. 1. Presence of carbon molecules. The identification of methane and carbon dioxide aligns with previous findings from the Hubble Space Telescope, indicating a consistent chemical profile across observations. 2. DMS detection. The potential discovery of DMS is particularly exciting as it is a compound that on Earth is produced exclusively by living organisms. However, its detection requires further validation to confirm its biological origin. 3. Implications for Hycean worlds. Researchers suggest that K2-18b could be classified as a Hycean world, a type of exoplanet that may harbor oceans of water beneath a hydrogen-rich atmosphere. This classification opens new avenues for understanding environments that could support life. For cautious optimism. While the findings are promising, scientists caution that these results should be interpreted with care. Non-biological processes could also produce the detected molecules, and further research is essential to ascertain their origins. Differences in perspectives. The scientific community presents a spectrum of interpretations regarding these findings. NASA's perspective. The NASA report emphasizes the technical aspects of the findings and the potential for future studies, highlighting the advanced capabilities of JWST in analyzing exoplanet atmospheres. Skeptical views. Articles from astronomy.com express skepticism about the likelihood of life based solely on current evidence, stressing the complexity of confirming atmospheric compositions and the need for more robust data. Controversy over DMS. Techno-science.net explores the contentious nature of the DMS discovery, noting that while some researchers advocate for its significance, others argue for a non-biological origin, such as the possibility of DMS being delivered by comets. Timeline of key events. 2015, K2-18b is discovered by NASA's K2 mission. 2019, the Hubble Space Telescope detects water vapor in K2-18b's atmosphere, suggesting liquid water. September 2023, JWST identifies methane and carbon dioxide along with a tentative detection of DMS. April 2024, plans for additional JWST observations are announced to confirm DMS presence and further investigate K2-18b's atmospheric conditions. Future research directions. The next steps in K2-18b research involve follow-up observations using JWST's MIRI mid-infrared instrument spectrograph, aimed at confirming the presence of DMS and enhancing our understanding of the planet's environmental conditions. Scientists remain optimistic about the potential to identify life on habitable exoplanets, a discovery that could profoundly alter our perspective on life's existence in the universe. Conclusion: the findings related to K2-18b represent a significant leap forward in exoplanet research, offering tantalizing clues about the potential for life beyond Earth. As scientists navigate the complexities and uncertainties of atmospheric analysis, the cautious optimism surrounding K2-18b reinforces the importance of continued exploration and observation. This research not only deepens our understanding of Hycean worlds but also fuels the age-old quest to answer the profound question: are we alone in the universe? The exploration of K2-18b has sparked significant interest in the scientific community due to its potential biosignatures. Yet there are numerous counterintuitive elements regarding its findings and implications. Here are some key counterintuitive aspects. 1. Presence of molecules does not equal life. The detection of methane, carbon dioxide, and the suggested presence of dimethyl sulfide DMS are often interpreted as potential indicators of life. However, the existence of these molecules alone does not confirm biological activity. As noted in the discussions surrounding K2-18b, non-biological processes can also produce these substances. For example, methane can result from geological activities, and DMS has been detected in comets, suggesting it can form without life. 2. Cautious optimism versus overenthusiasm. The scientific community exhibits a dichotomy in interpreting the findings from K2-18b. While some researchers advocate for a cautious approach, emphasizing the need for further validation, others promote a more optimistic view regarding the implications of the detected molecules. This tension reflects a broader debate within astrobiology about how to interpret ambiguous data. Despite the promising results, there is a strong consensus that the presence of certain molecules does not necessarily indicate a habitable environment or the existence of life. 3. Hycean worlds as a focus. K2-18b has been categorized as a Hycean world, which are believed to be more conducive to life than smaller rocky planets traditionally prioritized in the search for extraterrestrial life. This classification challenges the conventional perspective that only terrestrial-type planets can support life. The idea that larger, gas-rich planets might also harbor life due to their unique atmospheric conditions and potential for liquid water is a significant shift in astrobiological theory. For complexity of atmospheric analysis, the method used to analyze the atmosphere of K2-18b involves observing light from its host star passing through the planet's atmosphere. This indirect observation process is fraught with complications, as multiple gases can absorb light at similar wavelengths, making it difficult to isolate specific molecules. The analogy of trying to identify a single color in a glass filled with multiple dyes underscores the inherent challenges in confirming the presence of DMS or other compounds. This complexity is often underestimated in public discourse about exoplanet studies. 5. The role of advanced technology. The James Webb Space Telescope JWST has enabled scientists to make these groundbreaking observations. Yet the results are based on just a couple of transits. The precision gained from JWST's capabilities is remarkable, but it also highlights the fact that our understanding of K2-18b is still in its infancy. The reliance on advanced technology to produce potentially life-changing discoveries raises questions about how much we can truly infer from initial findings. 6. Scientific debate and divergence. The ongoing discourse about the implications of K2-18b's atmosphere showcases the divided opinions within the scientific community. Some researchers are calling for more rigorous standards for confirming biosignatures, while others argue that preliminary findings should not be dismissed. This division illustrates a fundamental aspect of scientific progress where contrasting interpretations can coexist and drive further research. 7. Non-biological explanations for DMS. While DMS is primarily associated with biological processes on Earth, its potential non-biological origins complicate the narrative surrounding K2-18b. This possibility challenges the assumption that certain molecules are definitive indicators of life and emphasizes the need for a more nuanced understanding of chemical processes in extraterrestrial environments. 8. The distance factor. K2-18b is located 120 light-years away, presenting significant challenges in confirming findings and understanding the planet's conditions. The vast distance means that even slight errors in data interpretation can lead to vastly different conclusions about its habitability and potential for life. In conclusion, while K2-18b's findings are groundbreaking and stimulate great excitement in the search for extraterrestrial life, they also come with a host of complexities and counterintuitive elements that warrant careful consideration. The scientific community continues to explore these findings with both optimism and skepticism, illustrating the intricate nature of exoplanet research. In the recent investigations surrounding the exoplanet K2-18b, several important content points have emerged that many people may overlook, yet they hold significant implications for the field of astrobiology and the search for extraterrestrial life. 1. The significance of dimethyl sulfide DMS. One of the most intriguing findings is the potential detection of dimethyl sulfide DMS in the atmosphere of K2-18b. DMS is a compound that on Earth is primarily produced by phytoplankton and is seen as a strong biosignature indicating biological activity. The tentative detection of DMS on K2-18b is significant because it suggests that there may be similar biological processes occurring on other planets. However, the detection is still under scrutiny, with some scientists suggesting that DMS may have non-biological origins, such as from comets or other celestial bodies. This debate highlights the complexities involved in interpreting biosignatures and the need for rigorous validation of findings. 2. Cautions in interpretation. While the presence of methane and carbon dioxide in K2-18b's atmosphere aligns with the possibility of a habitable environment, the scientific community stresses caution in interpreting these results. The existence of these gases does not necessarily imply the presence of life; they could also arise from abiotic processes. The ongoing discussion about the reliability of atmospheric analyses underscores the challenges astronomers face in confirming the presence of life-supporting conditions on exoplanets. 3. Unique characteristics of Hycean worlds. K2-18b has been categorized as a Hycean world, a type of exoplanet characterized by a hydrogen-rich atmosphere and the potential for large oceans of water. This classification is significant because it expands the criteria for what constitutes a potentially habitable planet. Traditionally, the search for extraterrestrial life has focused on rocky Earth-like planets, but Hycean worlds may offer environments conducive to life that are markedly different from our own. Understanding these unique planetary types could lead to new strategies in the search for life beyond Earth. 4. Technical challenges in spectroscopy. The method used to study K2-18b's atmosphere involves spectroscopy, where light from the host star passes through the planet's atmosphere, allowing scientists to infer the chemical makeup based on absorption lines. This technique is not without its challenges. The presence of multiple compounds can complicate the spectral data, leading to potential misinterpretations. The difficulties inherent in detecting specific molecules and confirming their presence highlight the need for advanced techniques and continued observations for more conclusive evidence. 5. Implications for future research. The ongoing research and upcoming observations using the James Webb Space Telescope JWST are crucial for confirming the presence of DMS and further characterizing K2-18b's atmosphere. The scientific community is divided on the implications of the current findings, with some advocating for a cautious approach and others urging further exploration of even tentative biosignatures. This divergence reflects a broader tension in the field about how to balance optimism with scientific rigor, which will influence future investigations and the prioritization of exoplanet studies. 6. Potential for discovering new forms of life. If future observations confirm the presence of DMS or other biosignatures, It could fundamentally change our understanding of life in the universe. The existence of life on K2-18b would suggest that life can thrive in environments vastly different from Earth, prompting a re-evaluation of the conditions necessary for life and potentially leading to the discovery of entirely new biological processes. In summary, the findings regarding K2-18b underscore the intricate relationship between atmospheric chemistry and the search for life beyond Earth. The potential presence of DMS, the unique characteristics of Hycean worlds, and the technical challenges of atmospheric analysis are all significant aspects that warrant attention. These elements not only shape our understanding of K2-18b but also have profound implications for the future of astrobiology and the quest to uncover the mysteries of life in the cosmos. The recent studies surrounding the exoplanet K2-18b have sparked significant interest in the scientific community, especially regarding its potential to harbor life. Here are the 4 most valuable points from the content provided which merit in-depth analysis and discussion. 1. Detection of carbon-bearing molecules, methane, carbon dioxide, and dimethyl sulfide DMS. The detection of methane and carbon dioxide in K2-18b's atmosphere by NASA's James Webb Space Telescope JWST is pivotal as it aligns with previous findings by the Hubble Space Telescope. The presence of these carbon-bearing molecules is essential for the assessment of the planet's potential habitability. The hypothesis that K2-18b may possess a hydrogen-rich atmosphere overlying a water ocean is bolstered by the absence of ammonia, which is often a byproduct of non-biological processes. Moreover, the potential detection of dimethyl sulfide DMS, a compound produced by life on Earth, adds a tantalizing possibility of biological processes at work. However, it is crucial to note that DMS's presence is currently tentative and requires further validation. This discovery raises questions about the methods used to analyze exoplanet atmospheres, the reliability of the data, and the implications of finding such biosignatures. The significance of these findings lies not only in the individual molecules detected but also in what they collectively suggest about K2-18b's environment and its capacity to support life. 2. Hycean worlds, a new category of exoplanets. K2-18b is categorized as a potential Hycean world, an exoplanet type characterized by a hydrogen-rich atmosphere and extensive oceans. This classification shifts the paradigm of the search for extraterrestrial life from focusing solely on rocky Earth-like planets to considering these larger ocean-covered worlds. The implications of this new category are profound, as they may expand the types of environments deemed habitable. This understanding encourages researchers to explore a wider range of celestial bodies when searching for signs of life. The emphasis on Hycean worlds also highlights the need for more sophisticated observational techniques and models to study their atmospheres, as these worlds do not exist in our solar system, making them challenging to understand. 3. Cautious interpretation of biosignatures and non-biological processes. While the findings related to K2-18b are exciting, the scientific community stresses the need for cautious interpretation of potential biosignatures. The possibility that the detected molecules could arise from non-biological processes complicates the narrative surrounding the search for life. For instance, while methane and carbon dioxide can suggest biological activity, they can also result from geological or chemical processes. The debate around the detection of DMS exemplifies this uncertainty, as some researchers propose non-biological origins for DMS, arguing it could be formed through natural processes unrelated to life. This discourse emphasizes the importance of rigorous validation and the need for multiple lines of evidence before concluding the presence of life. The challenges associated with confirming atmospheric compositions also highlight the limitations of current technologies and methodologies in astrobiology. 4. Future research directions and observational strategies. The findings regarding K2-18b open up several avenues for future research. Planned observations using the JWST and other telescopes aim to confirm the presence of DMS and gain a deeper understanding of the atmospheric conditions on K2-18b. These upcoming studies are crucial as they can provide further insights into the planet's composition, temperature, and potential habitability. The ability of JWST to analyze atmospheric spectra is a significant advancement in exoplanet research, allowing scientists to glean information about distant worlds with unprecedented detail. The importance of continued observations cannot be overstated, as they not only help validate initial findings but also enhance our understanding of how to identify biosignatures in the atmospheres of exoplanets more generally. This research could ultimately inform our broader quest to understand life's potential beyond Earth. Conclusion: the exploration of K2-18b represents a significant milestone in the field of exoplanet research. The interplay between promising findings and the cautious approach required in interpreting these results reflects the complexities of astrobiology. As we continue to refine our observational techniques and expand our definitions of habitable environments, K2-18b stands as a beacon of hope in the ongoing search for extraterrestrial life. The discussions surrounding its findings not only shape our understanding of K2-18b itself but also influence the broader landscape of astrobiological research in the search for life beyond our planet. 1. The discovery of phosphine on Venus 2020. In September 2020, a team of astronomers announced the detection of phosphine gas in the atmosphere of Venus. This finding raised significant excitement because phosphine is associated with anaerobic life on Earth. The discovery was made using data from the James Clerk Maxwell Telescope and the Atacama Large Millimeter Array. However, subsequent studies questioned the validity of the phosphine detection, suggesting that the signals could be due to other chemical processes. This case highlights the complexities and debates surrounding the search for biosignatures and the interpretation of astronomical data. 2. The detection of methane on Mars 2003. In 2003, scientists using data from NASA's Mars Express mission reported the detection of methane in the Martian atmosphere. On Earth, methane is predominantly produced by biological processes, which led to speculation about the possibility of life on Mars. However, further investigations revealed that methane could also be generated through geological processes, complicating the interpretation of the findings. The excitement surrounding the detection was tempered by the realization that non-biological sources could explain the observations, underscoring the need for caution in claims of extraterrestrial life. 3. The search for life on Europa ongoing. Europa, one of Jupiter's moons, has been a focal point in the search for extraterrestrial life due to its subsurface ocean, which may harbor conditions suitable for life. The presence of water ice and potential hydrothermal activity makes it a promising candidate for astrobiological studies. Various missions, including the upcoming Europa Clipper, aim to explore the Moon's surface and subsurface. The ongoing investigations into Europa's habitability echo the excitement and challenges faced with K2-18b as scientists seek to determine if life exists beyond Earth based on indirect evidence and complex interpretations of atmospheric conditions. The recent discoveries regarding exoplanet K2-18b, particularly the detection of methane carbon dioxide and a possible biosignature in dimethyl sulfide DMS, mark a pivotal moment in the ongoing search for extraterrestrial life. As we look towards the future, several predictions and insights can be made regarding the implications of these findings and the trajectory of exoplanet research. 1. Increased focus on Hycean worlds. The characterization of K2-18b as a Hycean exoplanet is likely to spur a new wave of interest in similar worlds, those that possess hydrogen-rich atmospheres and potentially vast oceans. Researchers may prioritize the study of Hycean planets in their quest for life, as these environments could provide the necessary conditions for biological processes. Future missions may target nearby Hycean worlds to expand our understanding of their atmospheres and chemical compositions. 2. Refinement of detection techniques. As the scientific community grapples with the complexities of atmospheric analysis, there will be a concerted effort to refine detection techniques. The James Webb Space Telescope JWST has already showcased advanced capabilities in spectroscopy, but future instruments may enhance our ability to identify specific biosignatures. Improved spectrographs could lead to more definitive atmospheric characterizations, reducing the ambiguity surrounding potential life indicators like DMS. 3. Continued debate and skepticism. The mixed interpretations of K2-18b's findings will likely continue, with some scientists advocating for cautious optimism while others call for rigorous validation of results. This debate over the significance of DMS and other biomarkers will push researchers to adopt more stringent criteria for classifying atmospheric signatures as indicators of life. The scientific discourse surrounding K2-18b will serve as a case study for future exoplanet discoveries, emphasizing the need for critical evaluation of claims. 4. Interdisciplinary collaboration. The complexities of exoplanet research will necessitate collaboration across disciplines, combining expertise from astrobiology, chemistry, planetary science, and even geology. As researchers seek to understand the potential for life on exoplanets, interdisciplinary teams will be essential for interpreting data and developing models that account for both biological and non-biological processes that could produce similar atmospheric signatures. 5. Broader implications for the search for life. The findings from K2-18b may broaden the scope of the search for life beyond traditional criteria. Instead of focusing exclusively on Earth-like planets, scientists may explore a wider variety of planetary environments, including gas giants and super-Earths that could harbor life in unconventional forms. This shift could lead to the discovery of life forms that do not conform to our current understanding of biology. 6. Public interest and investment in space exploration. The excitement surrounding potential biosignatures on K2-18b may catalyze increased public interest in space exploration and astrobiology. This could translate into greater funding and support for missions aimed at studying exoplanets, enhancing our capacity to explore distant worlds. Public engagement initiatives may also play a role in educating society about the significance of these discoveries and the ongoing quest for life beyond Earth. 7. Long-term missions and technological advancements. NASA and other space agencies may initiate long-term missions specifically designed to study K2-18b and similar exoplanets. These missions could involve advanced space telescopes or probes capable of closer examination. Technological advancements in propulsion and remote sensing could pave the way for more ambitious exploratory missions, perhaps even sending probes to these distant worlds in the coming decades. 8. Potential for broader cosmic perspectives. As we gather more data on K2-18b and its atmospheric conditions, we may gain insights that inform our understanding of life's distribution in the universe. The patterns observed in K2-18b's atmosphere could reveal parallels with other celestial bodies, allowing scientists to extrapolate potential habitable conditions and the likelihood of life elsewhere in the galaxy. Conclusion. The exploration of K2-18b represents a significant leap forward in exoplanet research and the search for extraterrestrial life. The findings have opened new avenues of inquiry, prompting scientists to refine their methodologies and expand the parameters of habitable environments. As we move forward, the interplay between optimism and skepticism, coupled with technological advancements, will shape our understanding of life beyond Earth. Ultimately, the ongoing quest will not only enhance our knowledge of the cosmos but also redefine our place within it.